Okay, so now that we have these values, let's just make a note right here that the p-value is much smaller for the latter because the curve has a much smaller spread and therefore a much larger test statistic. Let's think about that for a second. So notice the p-value on the second one is 0.0006, but the p-value on the first one is 0.731. Well, how does that happen? Well, we talked about it way back in chapter 8 a little bit. And keep in mind, it's actually two-tailed. That's why you can end up with 0.731, because it's actually this side and this side over here together. But suffice to say that this would be for like n equals 100, and this would be like for n equals 10,000. No, they're not to scale even remotely, but bear with me. Okay, so what's happening is that when you have a smaller spread, a larger spread, when you have a larger spread, then your test statistic is not as far out, and it means that your p-value is much larger, right? When you mush in the curve with a larger sample size, it gets crammed in there, so the area in the tail is minuscule, really tiny. Although technically it'd be two tails here, but it doesn't matter because they're so dang small that together they only make 0.0006 of the curve altogether. Okay? It's very much what we were talking about in chapter 8.1. Okay, but the difference of 4.4 to 4.5 is still really, really small, no matter how large n is. So taking a really large sample hyperinflates the significance of the difference. In other words, having such a large n shows us that the results is very statistically significant, right, when n equals 10,000. But in practical terms, the difference between 4.4 and 4.5 is negligible for most things. Now, of course, this gets into computer programming if you're into that kind of thing. There is a big problem with random number generators in that they're not so random, and that's what you're proving here. This random number generator from Excel or from a calculator is not truly random, but in the end, it's not different enough for us to really worry about most of the time, because it's only off by such a small amount that for most cases it doesn't matter. I mean, as long as we're not working with rocket science, we should be okay. Okay? And that's what I'm going to get to down here. So the practical implications are that when you have an n can have a very large effect on the standard error, which in turn affects the test statistic and the p-value. But we have to keep in mind that sometimes the difference in a practical sense is not that great, and the very large n values skewing our vision of what's important. This gave us this really small p-value, and you're like, oh, that's big, that's significant, and it is, but it's statistically significant, but not practically significant. I mean, it's not that big of a deal if your random number generator is only off by a little bit, right? All right, so what insight do we gain from this? Sometimes when n is really large, it can make us think that there's really significant things happening, but they're not. It's statistical significance, but not a really big real life difference. And that's what these boxes down here are talking about. There's an idea that small differences between the statistic and parameter stated in the null hypothesis are statistically significant, but the difference may not be large enough. In other words, having a really small p-value, such as 0.00006, for example, is highly statistically significant, giving strong evidence against the null hypothesis. But it does not imply an important finding that really makes any difference to, for example, if you want to go use the rand between function in Excel. It's not really going to change how you do it, right? Okay. All right, we are done with 10.4, or 10.3, excuse me. Well, we're done with 10.4 as well. All we got to do now is 10.5 and 10.6, and I'll see you back here for those videos.